Let's talk about the turbulence amplifier. Have you ever wondered how machines make decisions? It's not always with wires and electricity. Sometimes it's with something as simple as a puff of air. That's where a super cool and kind of mysterious device called the turbulence amplifier comes into play. It's a special kind of switch, but instead of using an electrical current to turn things on and off, it uses a tiny, gentle stream of air. Imagine trying to keep a long, smooth stream of water flowing from a hose. That smooth flow is what scientists call a laminar flow. The turbulence amplifier is a master at controlling this kind of flow, using it to send signals and make things happen, all without a single spark of electricity. Now you might be thinking, Bill, why would anyone use air instead of electricity? That is an excellent question. Think about places where a tiny electrical spark could be very, very dangerous. Places like a factory that makes fireworks, a room filled with explosive gases, or even a hospital operating room where sensitive equipment is being used. In these environments, you need a way to control machines that is completely safe from causing a fire or an explosion. The turbulence amplifier solves this problem beautifully because it's powered by fluidics, the science of using liquids or gases to do work. It's a clever, safe, and surprisingly powerful piece of technology. So what exactly is this device? Picture a small tube or pipe. A very steady, very smooth stream of air is sent from one end to the other. This is our on signal. As long as that stream stays smooth and undisturbed, it travels straight to a sensor at the other end, but if a tiny puff of air, called a control jet, hits the main stream from the side, everything changes. That gentle puff disrupts the smooth flow, making it chaotic and messy. This messy state is called turbulent flow. When the flow becomes turbulent, it spreads out and misses the sensor entirely. That's our off signal. It's a switch controlled by a whisper of air. This simple but brilliant idea opened up a whole new world for engineers and scientists. It allowed them to build complex control systems like the brains of a robot or the logic for an assembly line without any moving parts or electrical circuits. The only things moving were the streams of air themselves. This made the systems incredibly reliable because there were no gears to break or wires to fray. The turbulence amplifier became a key component in a field called fluidic logic, proving that you can build smart machines using the fundamental principles of how fluids, like air and water, behave. It's science in action, and it's awesome. Let's travel back in time to the exciting era of the 1960s. This was a time of great innovation, with the space race pushing scientists to think in new and creative ways. It was during this period, at the Harry Diamond Laboratories in the United States, that the turbulence amplifier was born. A team of clever engineers, including pioneers like Raymond W. Warren, was looking for new ways to build control systems that were tougher and more resilient than the electronic ones of the day. They needed devices that could withstand extreme conditions like high radiation, intense vibrations, and massive temperature swings, conditions that would easily fry a normal transistor. The invention wasn't a single eureka moment, but the result of careful experimentation and a deep understanding of fluid dynamics. Ray Warren and his colleagues were exploring how jets of fluid interact with each other. They discovered that a very stable, low-pressure stream of air, that smooth, laminar flow we talked about, was incredibly sensitive to disturbances. Even a minuscule puff of air from a control port could trip it into a state of wild turbulence, effectively turning the stream off. They realized this on-off capability was exactly like an electronic switch or a relay, but it was made of nothing but flowing air. This discovery was a game-changer for a field that became known as fluidics. The turbulence amplifier was one of the first practical fluidic logic devices. It could perform basic logical operations like AND, OR, and NOT, which are the fundamental building blocks of all computers and control systems. By connecting multiple turbulence amplifiers together in clever arrangements, engineers could create circuits that could count, remember information, and make decisions. They built entire control panels for industrial machinery and even early medical devices using these air-powered switches, creating systems that were incredibly robust and safe for hazardous environments. The team at the Harry Diamond Laboratories didn't just invent a single gadget, they helped launch a whole new technological field. Their work on the turbulence amplifier and other fluidic devices showed the world that complex logic didn't have to be electronic. It proved that the principles of fluid mechanics, which had been studied for centuries, could be applied in a revolutionary new way to process information. This legacy of thinking outside the box and using fundamental science to solve tough engineering problems continues to inspire inventors and scientists to this very day. Consider that, science. So, let's get down to the nitty-gritty science of it all. How does a tiny puff of air have so much power over a bigger stream? It's all about the difference between two types of fluid flow: laminar and turbulent. Imagine you're pouring honey very slowly. It flows in a smooth, elegant, and predictable sheet. That's laminar flow. The particles of honey are all moving in parallel layers, like cars staying perfectly in their lanes on a highway. In a turbulence amplifier, the main air supply is set up to be in this perfect, low-pressure laminar state as it travels down a tube. This is the default on position where the airstream successfully reaches a collector at the other end. Now, let's introduce a little chaos. Think about what happens when you turn a fire hose on full blast. The water sprays out in every direction in a messy, chaotic, and unpredictable way. That's turbulent flow. The particles are tumbling over each other, creating swirls and eddies. In our amplifier, a very small control jet of air is aimed at the side of the main laminar stream. When this control jet is activated, its energy is just enough to disrupt the delicate balance of the laminar flow. It's like gently bumping the first car in a long line of traffic, causing a chain reaction of swerving and chaos down the line. This transition from smooth to messy is the secret to the switch. When the main stream becomes turbulent, it loses its focused energy. Instead of traveling in a straight line to the collector, the air spreads out and its pressure drops significantly. The collector, which is designed to detect the specific pressure of the laminar stream, no longer senses the signal. The stream has effectively been deflected and dissipated, so the output reads off. The most amazing part is the amplification. A tiny amount of energy from the control jet can switch off a much more powerful main stream. That's why it's called an amplifier. A small input controls a large output. The beauty of this design is its simplicity and lack of moving parts. An electronic switch has physical components that can wear out, stick, or break. A turbulence amplifier has none of that. Its only moving parts are the fluid particles themselves, the molecules of air. This makes it incredibly reliable and gives it a very long lifespan. It can be switched on and off millions or even billions of times without any wear and tear. This is a perfect example of elegant engineering, where a deep understanding of physics allows us to create a powerful tool with remarkable simplicity. You might be thinking that with today's tiny microchips and powerful computers, a device like the turbulence amplifier is just a piece of history. And it's true that electronics have taken over most of the jobs that fluidics once did. However, the principles behind this amazing invention are far from obsolete. The turbulence amplifier and the field of fluidics are critically important in situations where electronics just can't survive or aren't safe to use. Think about the inside of a jet engine or a nuclear reactor. The intense heat and radiation would destroy conventional electronic sensors in an instant, but a fluidic device made of tough metal or ceramic can handle it. These devices are still the heroes in many industrial and aerospace applications. For example, they are used in controlling the flow of fuel in rockets and jets, where reliability is a matter of life and death. They're also used in hazardous material handling, controlling robotic arms that work with explosive or corrosive chemicals. In these settings, the fact that fluidic circuits don't produce any electrical sparks is a massive safety advantage. Another incredible use is in certain medical devices like ventilators and artificial hearts, where the gentle and precise control of air or fluid flow is essential for a patient's breathing and circulation. The legacy of the turbulence amplifier also lives on in a modern field called microfluidics. Scientists and engineers have taken the basic idea of controlling tiny fluid streams and shrunk it down to a microscopic scale. They create labs on a chip that use incredibly small channels and fluidic switches to mix chemicals, analyze blood samples, or test new medicines. These tiny devices can perform complex experiments using just a single drop of fluid. This technology is revolutionizing medicine and biology, and it all grew from the foundational ideas developed by the fluidics pioneers of the 1960s. So, the amplifier's spirit is very much alive. In the end, the turbulence amplifier is more than just a clever switch. It's a powerful reminder that there are many different ways to solve a problem. It teaches us that sometimes the most elegant solutions come from looking at the world through a different scientific lens. In this case, the lens of fluid dynamics instead of electronics. It pushed the boundaries of what was possible and created technology that is incredibly robust, safe, and reliable. So the next time you see a smooth stream of water or feel a gentle puff of wind, remember the hidden power of fluidics and the awesome science of the turbulence amplifier.